This conference will now be recorded.
All right, well, welcome back everyone for round 2 of 4 for our NERRS Ecosystem Metabolism R training. As I said a second ago, it's really great to see people coming back, which implies that you still want to learn from me and you want to learn more about how to use these tools. So it's always encouraging. I'm going to do just another quick rundown of what we're trying to do with this course and some housekeeping rules just to remind everybody of where we're at and why we're doing this. As I said last time, these trainings are part of an NSF-funded project with Doctors Ray Nadger and Wade McGillis and Jill Ariola and Maria Herman. They're all working with me to develop some tools to help us better understand and estimate ecosystem metabolism and using the NERRS data to do that. And so one of the goals of this training is to facilitate the tech transfer of those tools to you all, since you guys are going to be some potential end users of these products. The methods we are developing are going to be expanded upon and improved. So what we're going to be teaching you in these courses are basically things that already exist. So we're trying to give you a foundation and a foothold for continued learning as we continue to develop these tools through the course of this project. So I think, we've all got the software installed. Just like last time, we have RStudio Cloud as an option for you to use, but in the long term, you're going to want to use your own installation of RStudio, since that's a place where you can go back to over time and install your own packages and save your own scripts. So, but either one works for this training. We have this live coding link from last time. You'll notice that there's some code on here from the previous session. And I want to keep that there just for continuity, but if you scroll all the way down to the bottom, you'll see I've made a new section here that's going to be the first thing we're going to talk about today, importing data with Swamper. So you can use this code to keep up with what we're doing as I'm going through the lesson, or you can just try to type as we go on your own RStudio console, but this is sort of meant to be a placeholder for you to go back if you ever get lost with what we're doing. What else? Oh, yes. Obviously, mute your microphones, but if you do have a question, feel free to speak up or type it in the chat. We have some able R users in the session today that can help with some questions. The thing that's different about this training today is this is going to transition from our basics to some more topical things specific to how we do detiding and how we use Swamper to read in data for detiding and moving forward using that for ecosystem metabolism. So some of the topics are kind of niche, but if you have some general R questions, you can ask them in the chat, or you can just verbalize them and I'll try to answer them as we go. Let's see. Oh yeah, I did have the recording from last time on the website. I sent that out in an email, but it's also, I'm going to put all the recordings for the trainings here under each of the agenda items. So this is the recording from last week. It's on YouTube. I can continue to send those out via email if you guys think that's helpful, but if I don't get them out on email, they'll always be linked here maybe a day or two after each of these trainings, so you can go back and view them. Because remember, the whole point of this is to, this is meant to expose you to some of these ideas and concepts, not to make you like 100% proficient, but to use this as a resource going back. So the website will be a resource, but the recording can also be used to support that for going back to that information and reviewing it. So that's why we're putting that out there. Yeah, so are there any questions about anything that we covered last time before I get into the content for today? Now's your chance. So everybody's an expert with R at this point in running functions. Remember one of my goals last time was to just get you up to speed, get you comfortable using R Studio, sending code to the console, understanding the output, saving objects in your workspace, installing libraries, loading libraries, all that fun stuff. Moving forward, now that you have that foundation, it should be easy peasy just to load the packages that we've already built and running the functions moving forward. So you should be able to do them, but I'm also going to try to impress on you all why we're doing these things. So not just understanding that we can use Swamper to load data, we can use WaitRegDO to detide data, but what is the theory behind that and when it works well and when it doesn't work well. So there might be a little more explanation this time about the methods and providing that context to you as you execute the functions, because as you all know with R, one of the dangers is you have the power to do these analyses, but it's on you as a studious analyst to understand what the functions are doing and the limitations of the results that they provide. And so there are a lot of limitations about detiding. There are a lot of limitations about ecosystem metabolism. And so I'm going to try to impress on you all of those things, as well as how to use the functions to address those different goals. So this one is going to be all about detiding. The lessons, the third and fourth lessons, we're going to get actually into how to estimate metabolism, but I wanted to start with detiding first because this is often a good prerequisite for estimating metabolism, because metabolism estimates rely on dissolved oxygen time series as well as some other time series. And if that DO time series is influenced by changes with the tide, that tends to violate some of the assumptions for the method. And so we actually wrote this paper a couple of years ago that is one attempt out of a few out there that try to remove that tidal signal from a DO time series. And so that's what we're going to go through today. So we'll start with using the Swamper package, how to use that to import and clean up and combine the data before you start the detiding process with WaitRegDO. I did send out these papers early last week. There's a lot more information here than obviously we're going to cover today, and even more information than you need to care about for using Swamper and detiding, but those are going to be like the resources that form the basis of all this information. So hopefully you've had a chance to look at that. But so these are the steps we're going to go through today. Loading Swamper to import the data. We have some sample data sets from Apalachicola and Sapelo Island. We're going to use the import local function to do that. We're going to clean it up with QA/QC functions and then combine water quality and weather data with the comb function. And so these two bullet points are all using things from the Swamper package. But then this next step, we're actually going to do some fairly minor data wrangling to format the data even further to prepare it to use functions in the WaitRegDO package. And then towards the end, I'll be talking about some of the fundamental functions that are in these packages to evaluate when detiding may or may not work well, and then how to use the functions to actually do detiding. And as I said a second ago, I'll talk about a little bit how this works. So hopefully you kind of get an understanding of what's going on underneath the hood. And more importantly, when you should be skeptical of the results. And so this is going to be actually an ongoing theme in this lesson. In the next one is that these tools are good, but they don't work all the time. And so you need to get an appreciation for when they might not work as well as you hope they do. So a lot of baggage coming with these things. So a little bit about Swamper. This package was something that we developed a couple years ago. I haven't really been actively developing it in the last few years. Kim has helped a lot with this package, Carrie and Dave as well. But there's actually been a lot of interesting evolutions coming out of this package moving forward. There's been the Swamper extension package, and I've actually heard there's some new ones coming out as well that are building off of that. There's one that's going to look at like swamper storms or something like that. I think this is all new stuff that's being actively developed. But what's cool is that, this swamper package was kind of the foundation for these other things moving forward. And when we first developed swamper, it was kind of meant to just be this tool to facilitate ingestion of data into R so you can answer very general questions about what's going on at my site or my reserve. And it does that with some level of success, but I think the more value that we have with this package is that you can use it to import the data very quickly, which I think was a kind of a hurdle before. So that's why we're going to talk about the import local function, the QA/QC function to clean up those data once you import it, and then the combine functions to clean that information or combine data sets once you have them in there. But that's all we're going to talk about. There are other functions in the package that may or may not be relevant depending on what you want to do, but this will at least get you into place where you can have your data into R. So this import local function, as you know, there's a lot of ways to get swamp data from CDMO. And we were just like, let's just use one of these ways to import the data. So this function works with data that's downloaded through the zip downloads feature of the advanced query system. So hopefully you are familiar with that and what that means. But basically, if you go to the CDMO website, you'll eventually end up on a page like this. If you go to the advanced query, let's see, get data. Somewhere in this website, you get to this web page. This is the zip downloads feature, and essentially you just click on stations and you submit, and you'll get emailed a zipped file with all of the data. It'll be a zipped file with a lot of CSVs, some Word documents, but mostly just a lot of CSVs. And so this import local function, you basically just point R to where that file has been downloaded, and you name the station you want to import from that folder that you've already downloaded. So this isn't really a direct link to CDMO. You have to download the data first, but once you have it downloaded on your computer, you can use this function to pull it in quickly. So I'm going to go to my live coding link, actually my RStudio with the live coding script on there. So first and foremost, I need to load Swamper. So that way we can use the functions. If you are using your RStudio installation locally, you'll have to install Swamper already, of course. If you're using the cloud, it's already on there, so no worries. But at any rate, you load the package first, and then we have this import local function. We'll look at the help file. Import local. You'll see there's a handful of arguments that it takes, but the two most important ones are going to be the first two, where the files are and what the station code is you're going to import. And because I'm in a project here, remember we talked about RStudio projects last time and how where R looks within a project is relative to the home of that project, so your working directory. So this is my working directory. It lives on my C drive in this folder called EcoMetab training. But in this project working directory, there's a folder called data. You should have that. This is what we downloaded last time. This is where we unzipped all the data files. Basically, I'm telling R to look in this folder, in this relative path data, and I'm telling it to install, or rather import all of the files from the dry bar station of Apalachicola. So APA DBWQ, so it should be importing 3 different files because CDMO separates them into year when you use this feature. So I will run that. It will take a second because it's doing a lot of imports on the back end. It's doing some minor formatting, then it's combining everything. The one object, when it's done, I've assigned it to the APA DBWQ object with this assignment operator. I can look at the first 6 rows. And so this is when you import data with this function, it will almost always have this appearance. You have a date time stamp column with the date and time, and then one to many of the parameters that are measured for water quality at these locations. And what's you'll need to note is that for each one of these parameters, there's a second column that accompanies that column that is preceded by F underscore and then the name of the variable. So here's the temperature column and here's F underscore temp. And what this column is going to be a list of QA/QC flags that define essentially how you should treat that observation. Do you trust it? Is there something wrong with the instrument? Is it out of range? Is it historic data? Has it been corrected after the fact? So any of a number of things. And so what we'll talk about in a second is how to deal with those flags, because you might not want to keep all the data that have different QA/QC flags depending on what you're doing in your analysis. So your data look like this. This particular object has 105,000 rows and 25 columns. Again, the date range is 3 years of data, so 2017, January 1st to the end of 2019. So a lot of data at 15-minute time steps. And what's cool about this is, you could, in theory, do the same thing with read underscore CSV or read.csv, any of the other generic import functions you get in R, but you would have to do this manually to import one file at a time for every year of data, and you'd have to combine them after the fact. So import local kind of takes care of that takes care of that for you, so you don't have to spend a lot of time doing that by hand. And then also, just as an aside, it imports the data as a Swamper data object. So if you look at the class of that object, it's a Swamper class as well as a data frame. So it behaves just like a normal data frame. But this Swamper class is a class of objects that the Swamper package recognizes, and every single function in this package has methods designed to work with data of this type. And as I said, these are basically a data frame, but there's a set of attributes that come with each Swamper object that define different things about it. So there's a station name, lists of parameters, whether or not it has QA/QC columns. These are basically just things that are tracked with each object that the different functions can use depending on what it's doing. So that's just sort of an aside about how the Swamper package works. But for all practical purposes, you can treat this as a data frame. All right, so next thing we want to do is think about how we want to clean up these data. So again, we want to treat the observations with a little bit of care because each observation has a QA/QC flag associated with it. And before we run an analysis, we want to screen these observations based on the different flags because some of these data might be out of range or they've been corrected. Maybe we don't want to use those. It really depends on what you're doing for your analysis. But this QA/QC function will let you do that. And before I explain how it works, I want to show you this website. And I'm just assuming you guys probably know this already, but never hurts to look at the QA/QC flags again. But these are the integer values you get. And there's a whole bunch of sub codes as well. And you can actually screen by these sub codes as well. But for the most part, at least when I've ever used this function, I've just screened by the integer values, and typically I keep things that are essentially positive values or zero only. So things that pass initial checks or things that have been corrected. It's really up to you, but this QA/QC function will give you the ability to do that in one line. So I'm going to run that. So I'm going to run the function on the data object I just imported, and the argument that tells you which QA/QC flags to keep is this QA/QC underscore keep argument, and you put as options to that argument the flags as character strings that you want to keep. So if you're on keeping the flag 0, 1, 2, 3, 4, and 5, and then I could run that. And if I look at the resulting object, you'll see that it's the same, except now all those extra columns with F underscore parameter name have been removed. And it's a little hard to tell to go through the data, but essentially everything that didn't have these flags 0, 1, 2, 3, 4, and 5 are assigned an NA. So that's what this is doing. It's not removing entire rows. It's going through each individual observation and saying, okay, if we told the function to keep things that have these flags, it keeps them. If that flag isn't there, it gives it an NA. So everything that had a -5, -4, -3, whatever, is given an NA. Is that clear? All right.
Hey, Mark,
Yeah, go ahead, Dave.
if I told it to keep ones, for instance, and some of those ones also had those modifiers, does it keep ones plus modifiers, or do I have to specify that separately?
It keeps everything that has a 1.
Perfect. Thanks.
So 1 and then whatever modifier it has. And if you're used to using like regular expressions, that's kind of how you can filter by some of these other modifiers. And I think I have some examples in the help file that explain that a little bit.
Okay.
Yeah, so here's if you want to keep everything that had CSM as the modifier, no matter the number. But if you wanted like 1 and the CSM, you have to combine them with a regular expression, which is a little bit extra, but I think, yeah, you basically just combine them with this horizontal OR operator, if you're familiar with that. So that's pretty straightforward. Oh yeah, the other thing I wanted to point out is that, as I said, I'm not removing any rows with QA/QC, so the number of rows are the same as the original, so about 105,120. Here's the original. It's just removing those columns for the flags and giving NA values to the observations that didn't correspond to the ones you wanted to keep. And then, of course, the date ranges are the same. All right, so that's water quality. This function, the import local function and the QA/QC function, they work the same on the nutrient data as well as the weather station data. So I'm going to do the same thing for weather. PA, ML, net, the right one. EBnet. Okay, so import local. I'm going to look in my data folder and I'm going to import station code APA EB net. So the EB weather station, I believe, okay, so yeah, there's another useful thing here that I forgot about. There's this argument called trace, which will tell you what it's doing as it's importing files. So it's loading files, and you'll sort of see progress as it's progressing on the console there. That's really only useful if you're importing like 25 years of data, if you don't want to sit here and watch and hope that it's going to be close to being done. But that's just a nice feature. Well, I think it's a nice feature that'll show you progress as you're importing. And then we're going to clean that up. And I'm going to keep these 6. So there's the weather station imported. still 15-minute observations, 3 years of data, and then a handful of meteorological stuff that we need for estimating metabolism. So I'm kind of walking you through a workflow here that you can think about before you use these functions to estimate metabolism, because we need both water quality and weather data to do that. So when that's said and done, the next thing we need to think about is combining these two data sets, because the functions, as I just said, use water quality and weather data. These functions were actually made before the dplyr package was around. So the join functions that are really easy to use in dplyr can do the exact same thing, but we have some functions in Swamper that will do the same thing for you, more or less. And because it's meant to work with some of the downstream functions in the Swamper package, for now it's probably okay to keep using these combination functions in Swamper. So we have this function called comb for combine, and essentially all it's doing is combining two different data sets imported using import local by the date timestamp column. So you want to match observations in time. There's two arguments to consider when you use this comb function. The first one is time step, and this basically tells you what time step do you want to retain in your combined data set. So if you want to retain, so these are 15-minute observations, the data we just imported. If you want to keep every single 15-minute observation, you would set time step equal to 15, so don't slice any of the data, keep everything. In practice, that's what you would want to do. You don't want to throw out any data. For the examples in this workshop, I'm going to do everything at 60 minutes just because some of these functions can take a second to run, and 60-minute observations, keeping only those will make the functions run a little faster just for the purpose of demonstration here. So in that case, I'm setting the time step to 60. And you'll see in the output, we get everything retained on the hour. It's not like averaging things up and down to each hour. It's just pulling out things on the hour. So you're removing some of the data. So the time step argument is the first thing to think about. And then there's the method argument that basically describes how you combine data that has ranges of time with different lengths. Now, for these data sets where we have data for 2017, 18, and 19 in both the weather and water quality data, it doesn't matter what method we use to combine them, we're going to get the same result. But if you did have two different data sets where one started before the other, or one was only a subset of the data within a larger part of the second time series, then this method will actually affect what you get as a result. So the method argument takes two options, a union or an intersect. So if you're familiar with like set algebra, union would just be, let me combine these two things and keep the entire range of time for both data sets combined. And then the intersect option would be just combine these things and keep the ranges of time shared only between the two different time series. Now, again, for these two things, water quality and weather, it doesn't matter which one we use. Intersect will give you the same result as union. But if you are combining other time series, just keep that in mind that what you use as that method of intersection will vary. And if you're familiar with the join functions in dplyr, this is a lot like inner join and full join. So intersect versus union, same principles, but just keep that in mind if you're mashing things up and you don't know the ranges of the date timestamps in each one. So what we'll do then is I'll show you how to quickly combine the weather with the water quality data. And I'm just going to call it APA. I call it APA DB if I want, but this is the only example in this exercise where we use data from Apalachicola, even though there's other stations. So I'm just going to call it Apalachicola. Usually running is a more informative name. But here I have comb function. The first two arguments are going to be the water quality data set and the weather data set. I could swap them it wouldn't matter. It would just affect which columns go first. But then I have what time step I want to retain, 60 minutes, so on the hour observations, and then union as my method for combining these two things. I run that, runs pretty quickly, and then look at the first 6 rows. Again, we have things only on the hour, and we have the water quality columns first, and then the weather column starting with air temperature coming second. And then dim first, let's see, 26,000 rows, 23 columns. Just for sake of argument, I'll use intersect. If I haven't been lying to you, they should give me the same results. Yeah, so because these time series are exactly the same, again, it doesn't matter if we use union or intersect. So now we're like almost to the point where we can actually start with the detiding functions. And I'm hoping that wasn't too much. I just threw at you. This is all sort of pretty basic stuff, importing data, cleaning up with QA, QC, and then combining it. But I'm gonna let you free, and I want you to try this same thing on the Sapelo Island data that comes in the data folder. So I have you import data for the DC station, water quality data, import data for the ML weather station, QA, QC them both. You can try different QA, QC flags if you want, doesn't really matter. This is just for exercises moving forward. And then combining them with the column function. And you can use a 60-minute time step or something larger. Actually, you can try 120, see if that helps, because we're going to use this again in following exercises to do the detiding, and that actually might speed it up a little bit. So any questions on that before I put 5 minutes on the clock and let you guys free? All right. Pull up my clock. And then we'll have at it. All right, so hopefully that wasn't too challenging. I did notice in the chat there was some good discussion about keeping censored data. My discussion of which flags to keep totally ignores which ones you should keep. I just sort of demonstrating how to use the functions. The point was brought up in the chat that things that are above or below detection, you really need to be careful in terms of whether or not you keep them, because whether or not they're in your data could really bias the averages or any sort of summary information you have from those data. I think that's going to be more of an issue for like some of the nutrient data that are commonly at detection than the water quality data. Just going off some basic experience I've had doing this, but nonetheless, just when you're actually doing these analyses, take special attention to look at your flags and at the very least plot your data when you're importing it to see if the values make sense visually, because that's going to be one of your more truer ways to check whether or not your data is in agreement with what you think it should look like. So let me just briefly go through the exercise. I think since there's no questions or comments, if there are questions, speak up, but I'm not hearing any right now. I'm hoping that this was pretty straightforward, but so SAP, DL, what did we call it? Let's see, DC and ML. Import local in my data folder, SAP DCQ. Send that down. We're going to pull in those 3 files. The weather one. Import that. Get those 3 files. Then we'll QA, QC. I thought it's been a while. I think there may have been an option where if you put null, it will keep all of them. Don't remember. We'll see. Yeah, so if you do want to keep everything, I think you can just put null. Not positive in that though.
That's what your documentation says.
Does it? Okay. That's past me. It doesn't remember what past me wrote, so you just have to trust past me, maybe not current me. Oops. What am I doing? I'm mixing my functions. All right. So yeah, essentially, I think if we just use the QA QC keep equals null, it just removes those flag columns. It doesn't filter anything if you want to go that route. Another thing that it might be worth mentioning is there's a function called QA QC check, which will give you a table of all of the QA QC flags and a count of each one in your data set. So I just imported the water quality data again because I wanted to look at the QA QC flags one more time. So I'm just going to put that up here. QA QC check SAP DC WQ. So it's kind of hard to view from the console. So what we'll do, we'll see if this works. We'll try to view a table in a separate tab. Okay, so this function is kind of good. It just gives you a sense of the counts of the different flags in your data. So we have the flag name here on the left column, and then each of the parameters that you have in your data set as the column names. And so what these numbers are is how many times, for example, this C depth column had this particular flag -2 and then the qualifier here, so 1700. And so you can kind of just scroll through here and get a sense of like, oh yeah, so there's 93,000 observations for depth that had a 0 flag, meaning it passed QA/QC checks. And that by far is going to be, you know, the highest count for flags. So this is kind of, I mean, it'll give you a sense of when you do keep flags, how many are going to be kept versus how many are going to be thrown out. If, for example, you didn't want to keep everything that had, you know, -3, just as an example. So this is the closest thing I can think of to giving you a sense of the distribution of the numbers of flags you have in your data set. And so hopefully that'll be helpful for you all if you're actually using these things in practice. All right, so that's exercise 1. Any questions on that before we move forward?
Can you show us that can you show us that QA/QC check code again really quick? I missed it.
It's in the live coding link, should be, if I saved it.
Thank you.
There's the function name, and then I just wrapped it inside of this view function to pull up a table up what is happening up here. Yeah.
Awesome. Thanks.
Yep. Okay, so we're like almost to the point where we can start detiding. What we want to do now is to load the weightreg.do package and look at an example file that comes with that package so we know the format of the data to use with the functions. So 2 functions we'll be using in this example are eval core for evaluating correlations, and then weightreg for running the weighted regression to detide. You can think of eval core as something you would do as a diagnostic to evaluate periods of time when you think detiding may or may not work well. And then this weightreg function is the actual process of detiding. Both of these functions have inputs that are very similar in terms of the required arguments. The optional arguments are a little bit different for each one, but the required inputs are more or less the same. And you can actually look at the examples in the help files to see how we pull in that example data set and how to run the functions. Because remember, I think I mentioned last time that one of the things that I often do if I'm using a package for the first time to understand how its functions work is I'll pull up a help file and look at the examples at the end of the help file as a first check to see how I actually just get the thing to run. And that totally goes above understanding what it's doing, but that is often the first thing that I'll do. So we'll load do. Did anybody have any issues installing this package? Because remember, this is one that came from GitHub, and that could be sometimes challenging to install as opposed to getting it up CRAN. If you're using the cloud, it should be on there. So we'll look at eval core. Bunch of arguments here. These first 4 are going to be the ones you want to worry about. We'll get into that in a second. But if we go all the way to the bottom, we can see essentially this is how you would run a minimal example of how to execute this function. And sort of the same thing for weightreg.do. The data set I want to draw your attention to is this one right here, the SAP DC data set. This is one that comes with the weighted regression package. So if you load the package. Actually, this data set will be loaded behind the scenes, so you don't need to load the data itself. But I want you to look at this data set because this is the format that all of the functions, or at least the two we're looking at today, this is the format we need our data to be in. So we're almost there with the data we've imported. We've got a date timestamp column, we've got some water quality variables, and we've got some weather and tidal height variables. These are all things we get from the water quality and weather station data from SWAMP. But as with most things we need to be really careful about the case we use, so uppercase versus lowercase in the column names. We need to be really careful about spelling in the column names, and we need to be really careful about order, because 9 times out of 10, if that isn't right, actually 99 times out of 100, using a function, if that's not following a format the function is expecting, it will not work right. So the last step we need to do is just convert the data we've imported into this particular format. So this example file. And just as a general rule with any package, any function in any package, there's almost always going to be an example data set that comes with, or just a data set that comes with R to run a function. And so that's usually a good place to look first for just learning how to use functions in a package, is what are the inputs that it takes? Because remember, these examples are supposed to be standalone. So let's look at our data set. So the APA data set we created last time. So we'll see it's not quite the same as our SAP DC data set. And by the way, this is the same station I had you import for the last exercise. It's just some older data, but it's the same location. But we have, okay, we have date timestamp, that's good, but the casing is not the same. So this is using camel case, so upper cases with lower cases. Temperature, same, tidal case there. We don't need conductivity, we need salinity, but again, change the name, yada, yada. So basically we want to subset the columns we need and rename them. Now, there are obviously several ways to do this in R, but I'm going to have you use the dplyr package to select columns and rename them at the same time. Dplyr, as I said last time, is something that comes with the tidyverse. This is my go-to package for data wrangling. It is very effective, and the functions say what they do, so it's easy to remember what you're doing when you actually execute the function. And we're actually only going to use one function from this package. So we're going to use the select function, which lets you pull out columns that you want from an input data set and also rename them at the same time. There's actually a second function called rename that will do this, but you can actually accomplish this simultaneously by running select and then saying, I want this column, this column, this column, and then assigning it to a different name moving forward. So this is kind of like the assignment operator outside of a function, the less than sign and then the dash, but these are just arguments to the select function that basically say this new column name gets this column. So there's a couple steps in here, but essentially you're selecting and renaming at the same time. So rather than typing that all out, I'm going to copy and paste. And first I'm going to load dplyr. If you have the tidyverse installed, that should work, easy peasy. Load it, and then copy my examples. So here's the select function again from dplyr. I'm selecting columns from my APA object that I've already created, and I'm renaming them. So I'm selecting them in this order. So the order of the arguments in this function are going to determine the order of the output. So I'm selecting the 1, 2, 3, 4, 5, 6, 7, 8 columns I need to conform it to my Sapelo Island data set. So there's what I'm trying to make it look like. And I'm going to use the same naming convention. So this is a little tricky. You got to like look at your old data set while you're doing this to see what the old names are. That's why I kind of copied and pasted it rather than typed it by hand. But you can maybe look at this side by side. So I know this needs to go to this, and so I could type this as I go while I'm looking at the console. So you get the idea. But essentially, when I do that, execute it, and I look at the first 6 rows again, now it's looking a lot like the data set that runs with the examples in this package. So we should be very close to actually using these functions. So, you know, the precision is a little different on some of these columns, or at least how it's displaying them, but it has the same structure. And I can verify that if I want to look at the names, what I am trying to approximate. So this is basically testing for equality between the names. So if I look at just the names of Apalachicola, there's 8 names there. And I look at the names of Sapelo Island, 8 names there. And I compare them to each other with these 2 equal signs. This is how you test for equality in R, 2 equal signs, not 1. If I compare them to each other, I get true, 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 true. So this not only tells me if the names are the same, but if the order is the same. So this is kind of just a quick check to see if I've done it right. And if that is looking good, we can move forward and actually start using our functions. I think there was one more thing I wanted to mention. Oh yeah, missing data. So this is a whole other topic in itself. How do you handle missing data and analyses? What's kind of handy about our metabolism function is we need data for every single column, every single parameter. So if we have missing data for salinity, just salinity, for example, but we have temperature, observation, DO, air temperature, doesn't matter. We can't use that column or that row at all. So we can remove that whole row. Now with R, usually with missing data, a function will typically treat it 2 ways. Either 1, it won't work at all. It'll say here's missing data, or it'll give you some obscure error. Or 2, it will try to accommodate that for you. Like the mean function, for example, has an option to remove missing values, and you can treat the data accordingly. The weight reg DO functions fall in that former category where the functions just won't work if you have missing data. And so we actually have to remove this information before we went forward. And what I was saying about the fact that we need a value in every cell across the entire row, we can actually just remove entire rows at a time, as opposed to just, you know, well, I guess the alternative would be, I don't know, estimating with an average or something, but whatever. There is a simple function in R called na.omit that will remove missing values in a vector or a data frame or some other larger object. Now, with most applications of swamp data to metabolism, as I said, it's totally okay to remove entire rows because that will just be treated as a missing time step because you don't have all of the data we need to estimate that. So in this case, na.omit would work really well. And so I have some examples here, sort of walking you through that. So if I just look at the number of rows and columns in my data set, 26,000 rows, 8 columns. If I run na.omit APA and reassign that to itself, and I look at the same dimensions, you see it actually bonked off like half the observations in that data set. And this is actually because, I don't know if there's anybody here from Apalachicola on the call, but it seems like in 2019, there's a lot of missing data, and for whatever reason, it's just not in CDMO. And so when I ran NA-omit on this data set, it pretty much removed most of 2019. So totally fine. I mean, if there's missing data, there's missing data. Can't really do much about it, but just it kind of stops September 2018. But just kind of realize that that's a consideration for most functions in R, and especially for estimated metabolism, because you need an observation every single time step to use metabolism. All right. So exercise 2. Any questions on any of this before I set you free on exercise 2? I feel like I'm moving a little fast today because I want to get to the detiding part, but I don't want to move fast enough to confuse people. Any questions? All right. So this exercise, you'll take the object you created in exercise 1 for Sapelo Island, and you'll just run through the same set of functions we just did. You're going to select the columns to match the existing data set in the weighted-reg-DO package. So essentially, you can just copy and paste the example up here and change your inputs, and then run NA-omit to look at or actually remove those missing observations. And then you can compare how many you had before versus how many you had after you removed those. And so it should be pretty simple. So I'll put 5 minutes on the clock and let you add it. All right. Okay, so that hopefully was pretty easy. Same as before, as with the Apalachicola data. You'll notice that there's not nearly as much missing data at this site. So you should have had about 26,000 observations before you ran NAOMIT, and then lost maybe about 700 or so after you ran it. I totally forgot that the reason there's missing data at Apalachicola for that year is because of Hurricane Michael, which is mentioned in the chat. So that's a pretty good excuse to not have data for that year, unfortunately. So we won't be using that year in our exercises as a result. Now, this last part, it's easy to use the functions, as I said, for detiding, but what I want to do is just, again, sort of emphasize why you would want to use them and kind of explain a little bit about what they're doing so you understand some context to the results you're going to get from those functions. And we are going to spend some time next session going over ways to somewhat quantitatively evaluate the quality of these results using the estimates from the metabolism functions. You can't really do that very easily with the output from the detiding function because we're kind of using the metabolism results as an endpoint to verify how well detiding potentially worked, because that's just kind of the workflow we constructed for these data. So I'm not going to really explain too much about how you could tweak the inputs or the arguments to change the results. I'm going to save that for next time. But right now, you just sort of need to understand a little bit about how they're working and when you have faith in the results or not. So the whole reason, again, why we're doing this, why we're detiding, is that one of the fundamental assumptions of metabolism is that the DO time series that you're using to estimate metabolism is measuring the same water mass over time. So if you have water moving back and forth across the sensor with changes in the tide, you're not really doing that. You're measuring potentially something that is very far up the estuary to very far down the estuary as the tide changes, and you can't really say much about the metabolic history of that single location. More importantly, what tide does at a literal level is it really screws up the calculations for estimated metabolism. So these metabolism functions, at least the method we're using, assumes a diel daily curve for DO that essentially starts to go up as the sun rises. It maximizes around mid to late day, and then as the sun goes down, DO starts to decrease and eventually just goes to a minimum at very early in the morning as respiration processes kind of dominate. If you don't have that curve, you can't calculate metabolism because you get wonky numbers because it's based on essentially an integration of that curve. And this will manifest itself most often in the metabolism estimates as essentially negative values for production and positive values for respiration. I don't know if that makes a lot of sense at this point, but we want those signs to be reversed when we're actually estimating metabolism. And we'll talk about that more next time. Really, your first check to understanding whether or not the tide has influenced your DO time series is to make a plot. This shows essentially a 1 week or 10-day period at Sapelo Island, where you have DO on the top one and then tidal height on the bottom one. And actually, there was a question in the chat about where's the tide coming from? And yes, this is just the elevation vector measured from the sonde at the water quality site. So this is our proxy for tide. And what you can see here is that this is like a really good example of how these assumptions, how this is violated for metabolism, because you have the DO time series. It looks almost identical to the tide. These little orange vertical bars are periods when it's daytime, and in between it's nighttime. And so if this was a DO time series that we thought we could use for metabolism and we wanted to have that diel periodicity, we would see DO going up during the day decreasing during the night, up during the day, decreasing during the night. But instead, it follows the tide like so close it hurts. And so our whole motivation behind this process is to use these functions to remove the influence of the tide on this DO time series. If there's interest, I can maybe explain in a little more detail, or attempt to explain in a little more detail, how the process works. But essentially, we borrowed a method from Bob Hirsch and colleagues at USGS called moving window, weighted regression on time, discharge, and season. And we sort of modified that approach to apply to tidal time series. But this is all it's doing is it's a regression, and it's a regression that moves in a window from left to right in the time series. Within each window, it fits a unique regression to every single point by considering the contribution of where the center of the window is relative to the time of day, how many days you have to the left and right of the window, and the proportion of the tidal height that you're observing within that window. And essentially, it's a hyper-parameterized, smooth model of a regression that's fit to every single point in the time series that really predicts tide very well. But because it's hyper-parameterized, you have a lot of essentially betas or slope parameters for these components of the time series. You can estimate an influence of the tide on those results and normalize a time series by removing that influence, that signal of the tide on that point. That probably doesn't make a lot of sense, but you just have to trust me that it kind of works. And when it does work, it works well. When it doesn't work, it works horribly. And we need to be careful of understanding when it works well and when it doesn't work well. And we have different diagnostic tools to do that. And part of the reasons why it works well is there's certain times of the year that allow us to estimate that signal. And there's other times of the year where we can't. But there's also an effect of the width of the window we use when we're fitting that regression. And those parameters are going to be really important for driving how we're going to remove that tidal signal from the dissolved oxygen time series. And we do actually have quantitative measures to evaluate both of those things. For the window width issue, that is something we're going to tackle next time. But for this time of year type issue, that's something that we can tackle today. But what you want to get from this paragraph, this is my attempt at really describing something that this whole paper really does in a much better way. What you get from it is a so-called normalized DO time series. This is that observed time series that is the biology, the production and the respiration of the system, and the tidal signal in that observed time series. And you get a normalized time series after that, which is the detided time series that should be just the biological signal. So when we say normalized, we mean detided. When we say detided, we mean normalized. And we really are describing our attempt at isolating the biological signal of the DO time series, that production respiration signal that's a product of just how fast the wheels are turning in the system as a result of metabolism, not as a function of the tide. Are people hanging in there? Okay. So again, check out the references for a little more detail on the methods. But what I want to show you first is something that I think is easy to understand and a simple screening tool that you can use first for detiding. So as I said before in this paragraph, we have, there's certain times of the year when detiding will work well and other times of the year when it won't. And the times of the year when it won't work well, essentially you have a correlation between changes in the tidal height and the sun angle, because we're trying to remove the effect of tide. And if that's correlated with the sun angle, that means it's confounded with how that sun is influencing, how the solar respiration is influencing production. So that's just, you have sort of collinear terms in your regression, and you simply can't isolate the tide from the biological signal. And so we're using sun angle as a proxy for kind of biological signal here. And there's certain times of the year when those two things are going to be highly correlated. And in those times of the year, that's when detiding will not work well. You'll detide both the tide and the biology from the time series. The opposite of that is when those two things aren't correlated. So the tidal signal is moving at different directions relative to the sun angle, and we can actually use this method to pull out that tidal component without bonking out the production or the biology signal. And so we have a function to do this. It's called the Eval core function, which I'll show you in a second. But there's two more things I want to tell you about this first. Detiding is not the answer to everything. I've had people ask me how to do detiding, and usually I come up to them and I say, well, do you have a strong justification for doing it in the first place? And a place like Sapelo Island, I mean, this is a clear-cut example of why you would want to do this, but in other places like microtidal or mesotidal systems where the tide is there, but not super strong, I think you should really consider whether or not detiding is worth your time. And again, when we look at metabolism estimates, we have different ways to measure the influence of tide. And if those measures are telling you that it's not a big deal, then I wouldn't even bother with detiding, because if this tidal signal is not having influence in DO, detiding is going to cause more harm than good. And then lastly, it's an art. We have attempted to provide quantitative measures to do this, but there's basically just rules of thumb coming out of these quantitative measures that we try to follow, and there's no definitive answer of what is the best approach to using detiding. What is the best set of window widths we want to use to maximize our ability to detide and preserve that biological signal. So there's a lot of sort of back and forth when you're doing detiding and metabolism to look at the different measures. Always plot the data, kind of look at these diagnostic tools as well, and we'll get into some of those other tools next time. Any questions about that? I just explained a lot. I basically just summarized this paper in a really mashed up way, but this is kind of fundamental. And if we want to spend some time at the beginning of the next session going over some of these principles a little bit more, we can, but I just wanted to put these out there first. All right, so this eval core function, this is going to be your first sort of diagnostic tool to understand the times of the year when detiding is expected to work well and times of the year when it's not expected to work well. And so you run this function. I'm actually going to copy it over to mine. It takes a second to run, like a minute or two. So I'm gonna let it run while I explain what it's doing. But it uses as input the combined data set that we just made. So this APA data set that has the same columns and title case or naming convention for the columns. Then it uses the time zone it's in, which is an attribute you can take from the date timestamp column in your data input. Then it takes a location of that site. In this case, this is the location of the dry bar site at Apalachicola. And you can get that from the metadata files. There's some functions in Swamper that'll do that for you. But what this is doing is this function is testing the correlation between tidal height and the sun angle in, I think, 6-day windows from left to right in the time series to look for times of the year when those two things are correlated. And again, if they are correlated, those are periods of time when you can't isolate the tide from the biological signal. And so what that interpretation is in those times of year, interpret the detided results with a grain of salt, because they may or may not be doing what you think they're doing. And so this is the time series plot we get. And so here's zero correlation. So for this time series from about a year and a half, here, and here, where it's zero, are times when we can really kind of trust the detiding results. down here, up here, down here, and up here, when these correlations are maxed out, these are times when we might expect the results to not really detide what we think is being detided. So this is a period of time when the weighted regression is possibly removing both the biological signal and the tidal signal, because those two things are potentially confounded at those periods of time. So look at this, like when you're using this in practice, look at this plot and just remember when you detide the time series, the DO, the normalized DO here, 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 and here might not be what you think it is. And that goes as well for the metabolic estimates, because those estimates depend on the DO time series as well. So this is just like, you should just have this plot in your back pocket when you're running metabolism from detided results.
Hey, Marcus?
Yeah.
Yeah, before you leave that slide, so the magnitude of those extremes is kind of plus and minus 0.5 for a correlation. If that magnitude were just 0.25 plus or minus, is it, I mean, how important is that correlation with how well people should be trusting their results?
It's better to have it lower, and this is where the art kind of comes in. We, in that paper, didn't really draw a line in the sand. We kind of just said, plus or minus 0.2 is a general benchmark, but we don't really have any kind of quantitative justification for that. It's just, we had, so in that paper, we had 4 sites, and I forget which figure it is, but one of the sites has like almost 0 correlation for the whole thing. Another one punches above 0.25 at times. And just based on our interpretation of the results from those sites, we kind of said that, okay, the one that punched above 0.2, 0.25 plus or minus, we were getting some wonky results from the detided results. And we just said, okay, that's kind of the line in the sand where we're drawing. But I'm hesitant to say this is the number you should be cautious of, or you should say, I'm going to throw out these values, whatever. I would just say, if you do see wonky results for these periods of time, and wonky is a real thing that I can define next time, it's probably because these are periods of time when the things are either positively or negatively correlated, confounded in some way. Okay. So again, just keep this one in your back pocket. As I said, before you do detiding and metabolism, keep that there so you can interpret the results when you're ready to. But then, now we can actually go forward and use weighted regression to detide. So this is all it is. And this is kind of the danger of R, because you can do a lot with one line, but you got to understand what's going on a little bit underneath the hood, how to interpret the results. And that's why I spent 15 minutes explaining these things, so you can sort of not just use this without understanding that. So this also takes a minute or so to run, and it will take longer the longer the time series you have and the smaller the time step. This is why we did that 60-minute subset before. But it's not, as far as computational stuff in R goes, it's not that unreasonable. But we'll let it run. So again, takes the same data set as input, same time zone, the lat and long, and then we'll let it run. And so the reason this takes so long is it's fitting however many observations there are in this data set. This one had like, what, 15,000 or so. It's fitting 15,000 different regressions to this time series. And so that takes a minute. It's kind of a brute force way of fitting this, but it works reasonably well. So while that runs, I'll just explain the output. So this is what you'll get after that runs. So you'll see up until this column here, it's the same format as your input data set, but you have all these other columns that are either output used by the metabolism functions. Well, it's all used by the metabolism functions, or it's specific to the actual detiding process. So the thing I want you to look at carefully here is these last two columns. So these are going to be your predicted dissolved oxygen that should match fairly well to your observed DO. And then you have your normalized DO column, which is your detided DO time series. And we can use this one or the observed time series as input to metabolism functions moving forward, depending on how much we want to trust the detiding results. So we'll check, let me check R, see if it's done. Okay, it's still thinking. These, yeah, I don't want to talk about the rest of these columns. Just realize this normalized column is going to be the detided one. And I'll close by just showing you one simple diagnostic of what this looks like when it's done. As I said before, next lesson we'll have some quantitative measures to evaluate how well detiding has worked. And based on those results, we can sort of go back and tweak the inputs somewhat, maybe change the window widths to affect the outcome. But this is going to be your first cut of like what it has done. So this is, if you're not familiar with Plotly, this is just another plotting library. This is useful because it gives you interactive plots for zooming and stuff. And I find it really useful for these long time series because you can see the whole thing, but you can actually zoom in on different points and get a sense of what's going on at the daily scale, which is what we're most concerned about here with metabolism. So I'm not going to explain what all this does, but you can essentially just copy that into your code and it will do that for you. As a matter of fact, I will do that. So you have that. You'll have to install Plotly, of course. If you don't have it installed, it's on the cloud version, so you should be able to do it there. But this plot shows the observed DO in blue and the detided DO in orange. So let me just zoom in on a snippet. So two things here. This orange one, you can kind of see, at least visually, how now we see that at least the diel period is a lot more pronounced or visible. It's visually apparent. So like these troughs are going to be like early in the morning, typically. That one, yeah. So I don't know if this is the right. So these, yeah, here's sundown. Let's see, 7 o'clock at night. So production starts to drop off. This is early, late morning when production's lowest. So you can see the date and time as I hover over these things. So first thing to notice is that, yes, you see that diel signal a little more pronounced. And second, what will happen 99% of the time with detiding is the diel amplitude will be muted compared to the observed time series. And this may or may not be a good thing. This could be because we've actually pulled out the tidal influence, or it's because we've just bonked out a portion of the time series that's related to both biology and DO. So just be aware of that. And again, we have some tools at our disposal that I'll cover next time to sort of quantify how well or how much trust you have in these results. But I just wanted to first show this to you as a proof of concept for how this works in practice. So how are we feeling about that? Okay, we're right at 2:30. You're free to go. I don't want to keep you longer than I promised, but we do have one more exercise, which is essentially doing this with the Sapelo Island data set. So use the eval core function, look at the correlations, and then do the same thing, but run weighted regression on that time series, get the results, and if you're feeling super ambitious, you can run Plotly on it and see the results. So again, you're free to leave if you want, but I'll put 5 minutes up on the clock, and then we can stay an extra minute and discuss the results or anything about weighted regression you want. Sound good?
Our session aborted. Just sharing that in case anybody else feels bad.
Happens to the best of us, Dave. Are you using the cloud version or your local?
Local.
Okay. What did it break on?
Plotly for the last plotting or Yeah, plot like for the final results.
All right, so it's not my fault then.
No, it might have had something to do that I was resizing the window at the time too. So, you know, if it's worth using a software package, it's worth abusing it.
Well, yeah, and you're not really doing programming.
No.
So I was hoping my example would finish running so I could show you the plotly of Sapelo Island before we closed, but still thinking. If you are feeling ambitious, these functions, you can write them to work in parallel to like make use of multiple cores on your machine, programming or threads, cores, whatever they're called, processors, that's what I'm looking for. So you can make them run quickly. And this works pretty well if you have a longer time series. You can actually cut down your processing time quite a bit. And so a lot of the examples in the help file show you how to do that. And all you have to do is install the for each and do parallel packages. Yeah. And I think when you load WaitRegDO, oh no, here, I'm doing it right here. So this is the help file for Eval core. Yeah, but it's the same for weighted regression. So if you load this do parallel library and set up a parallel backend for your computer, you might have to change the argument for the number of cores. And it's usually not good to use all the cores on your computer because then you won't be able to do anything else while it's running. But if you set this up right, it should run in like a fraction of the time if it's a longer time series, and that could be helpful. So any questions on any of this? I'm letting my version run so I could maybe show you that plotly, but while I'm waiting, I can entertain questions about weighted regression or detiding.
I may have some questions for you after I try this out on my data because you know that's going to happen. But for now, I'm good. Thank you, Marcus.
All right. And I'm sure everything I explained was like so crystal clear and you guys are experts now. I'm just gonna like sleep well tonight knowing that I faithfully explained this. I've never actually taught the detiding stuff before, so you guys are my guinea pigs. I don't know if that was the most effective way to do it, but again, the important thing is to know how to use the functions and what are its limitations, just like any function in R. So hopefully I communicated that.
Definitely. I understood most of what you explained today, so I thought you did a nice job. And I had a quick question. Did you finish the eval core for Sapelo Island? And could you just show that plot really quick so I can compare to mine that just finished? I don't know.
I cut mine because it was taking too long. I wanted the run regression, but what I can show you is there's a figure in the paper for I think 2012 data or something from Sapelo Island. This is what I was talking to Dave about.
Anna, were your values all real low, like under the 0.2?
Yeah, like well under 0.2. It just looks very different than the first one we did.
Is it like this one?
Yeah, it looks like that.
Okay. Yeah, we loved Sapelo Island when we did this paper because it was not the problem child. It was Padilla Bay and Elkhorn Slough were the big offenders. And we haven't, really extended this analysis to many other stations. And quite honestly, one of the objectives of this NSF funded project is to really get a handle on how well this method works, among other things. You know, because I don't know if Wade's still on the phone, but he's an expert with field deployment of various instruments that can really measure how much the tide is influencing these things. And we want to compare those field results to this method so we can not only see how well or how bad it's detiding, but really make it better. I don't know what make it better will look like at the end, because it might involve, you know, supplement with additional data that might not be available for everybody, but at least we can, I think, have some more confidence in our conclusions this way.
Hey, Marcus, given that this is kind of a an additive detiding or subtractive, whatever, detiding approach, what do you think about the actual magnitude of the tides? Because and kind of a signal to noise ratio for the tides to the biological signal. Because, you know, Sapelo Island and that part of Georgia and this part of South Carolina have the highest tidal range on the East Coast, other than kind of until you get up to Bay of Fundy. You know, we're talking about a huge tidal range compared to a lot of these other places. And I'm wondering about GTM, how theirs going to work out, because I know Indian River and that have, you know, foot tidal ranges, and I don't know about you.
I thought, you know, that initially that, you know, the magnitude of the tide would have some influence on how well you could detide, but each place is so specific in how the correlations play out. And what's really tricky about these methods is, you know, when we talk about when things are correlated or not, you know, we can talk about the seasonal scale, but you oftentimes get into like a daily time scale as well, because these things are, you know, the tide changes 24 hours, you know, a few times, and there's just different scales of time you have to consider that we really couldn't make any general conclusions about, you know, macrotidal versus mesotidal or microtidal. You know, even like some of the Gulf sites were more problematic than some of the sites on the Pacific, you know, and those are two very different locations with how the tide affects circulation in these systems. And so we couldn't really have any like really well-defined rules of thumb, and we just had to take things on a case-by-case basis with this. So one other thing I was going to say about that. Oh yeah, and the location, latitude has something to do with it too, because that's why we use sun angle as a measure for the correlation, because north versus south, you know, depending on the time of year, that angle is going to hit different ways. And that really has an influence on productivity as well, and the extent that varies with the tide on an annual scale, monthly scale, daily scale. It's just really complicated, and even tides by themselves are like multi-different harmonics that it's just, I mean, we were surprised this worked as well as it did in cases where it did work, but not really totally surprised it didn't work at some of these other sites. And it's just a tool that we think works good enough, and you just have to know its limitations. And we're taking it as far as we can with, I think, the quantitative desktop exercises, and this NSF project is really trying to go beyond that and actually supplement some field data with some high resolution sampling, you know, with ADCPs and all that fun stuff to really narrow this down a little bit more.
Hey, Marcus, this is Wade. Just wanted to chime in. Yes, I am here.
Did I say everything right about what you do?
Yeah, I don't think you went into too much out on a limb, but the idea is to capture the different aspects of metabolism in all of the different compartments, whether it's looking at the production in the water column or in the substrate, or the gas exchange across the surface. And then the whole idea is to eliminate all the advection that comes in artifacts with the tide.
Yeah, and this project started just over a year ago. We were planning on doing field deployments last year, but just like everybody else, you know, we had to put that on hold. So I think, Wade, have you I don't know what the recent plan is, but I know last time we talked, we were going to do, we were seriously considering actually starting the field deployments at Apalachicola and Hudson Bay NERR.
Oh yeah. I mean, I'm actually in the Hudson River Estuary Station right now, but I will be doing next month, going out and doing a site review with Ethan and looking at Apalachicola, and as soon as everything goes in play for safety, we'll be starting summer, fall.
Cool. Yeah, so definitely more to come with this project. We're just getting started, and as I said before, we're just trying to get everybody up to speed with the existing tools, because I think we're going to have some really cool ones coming out of this project. So I think we should wrap up unless there are any more questions. Super. Well, again, thanks everybody for your time. I know we're over 17 minutes, but as always, hope it was useful, and reach out to me for questions, and I'll get the recording online probably tomorrow, and next time we'll dive more into the metabolism estimates. So thanks again.
Thank you.
And everybody.
Thanks.